Some of the hardest problems in the world exist far above the planet. Our job? To launch the smartest solutions, to protect our satellites, clean up our clutter, to propel breakthroughs in propulsion, to learn more about our place in the universe, to outpace emerging threats. Every day, the Aerospace Corporation uses the latest technologies to ensure our nation's safety and leadership in space.
Welcome to the Space Policy Show. We have a great episode for you today. We are talking about nuclear technology in space with Pat Maloney and Jim Howe. As always, feel free to ask questions. We are at hashtag the Space Policy Show on Twitter, or you can put your comment in the video box below. We would love to hear from you, so please ask any and all questions or comment and engage. We're happy to hear from you. Pat Maloney is a principal engineer with Aerospace Corporation's Civil Systems Group. She has an extensive background in oil and gas and has lived all over the world. She provides technical management, leadership, and insight across a variety of missions at NASA's Marshall Space Flight Center in the functional area of science and technology. Not only that, but she's been with Aerospace for 19 years. Our other guest, Jim Howe, is a doctoral candidate at the University of Leicester in the United Kingdom. His thesis topic is exploring the development of U.S. policies related to the use of peaceful nuclear technologies in outer space, and is tracing the history of American nuclear propulsion and power programs designed for space applications. He also served in the U.S. Coast Guard as a commissioned officer, retiring at the rank of captain. We're so pleased that you could both be here today. We're very excited to hear what you have to talk to us about. And without further ado, I will transfer it over to Pat to get us started.
Thanks very much, Rebecca. And Jim, thanks for coming on with us. I think what we'll do today is, as we talk about nuclear technologies, if you would maybe give a few minutes on the history so we can bring people up to where we are currently. So Jim, for a few minutes, a history lesson on nuclear power and propulsion.
Sure thing. Thanks, Pat, and thanks, Rebecca, and a special thanks to the Aerospace Corporation for allowing us to have this opportunity to talk about a really fascinating topic. A special shout out, of course, to University of Leicester for the great programs they have for distance learning, postgraduate and graduate studies, and to my two professors, Dr. Andrew Futter and Dr. Blood Bowen, who have been providing just great supervision to this project. I can't thank them enough. But, we really stand at the dawn of an exciting time for American space programs and for American space policy. If you look, we're going back to the moon. That's the plan, at least. We have Americans being launched aboard American spacecraft for the first time in many years. We've got incredible things happening in the private sector with space tourism on the cusp of being real. A lot of small providers for satellites and launch services. You even have Relativity, which is 3D printing an entire rocket assembly, which is a breakthrough technology. So a lot of great things happening. But on top of that, the U.S. government is again looking at nuclear power and propulsion systems for use in space. And I say again because we've done this before, been there, done that. Going all the way back to the 1950s, we've had 5 major programs for both nuclear energy for power and nuclear rocket propulsion programs, expending in current year dollars well over $10 billion, millions of man hours invested, and sadly, not a whole lot to show for it when it comes to operational assets. We've only launched a single, very small demonstration reactor into space. That was in 1965, so it's been a while. That was the SNAP-10A reactor. It operated for 43 days before a subsistence failure made it incapacitated. And on the nuclear rocket side, we've never really even done a flight test of a nuclear-powered rocket. Now, you've heard of the Rover and Nerva program back in the 50s, 60s, and early 70s. That's the longest-lasting rocket development program that we had. We actually tested 20 different reactors in the Nevada desert and got the technology all the way up to technology readiness level 6, which is one step away from deployment in space for testing. That's a pretty remarkable achievement. We also had a second program that happened in the 80s and 90s called Timberwind. It was a classified program under the Strategic Defense Initiative. which transmuted into a different program called SNTP, Space Nuclear Thermal Propulsion, under the Air Force's guidance, and that was defunded in 1994. And finally, most recently, we had the Prometheus project in the early 2000s, which was looking to use nuclear electric propulsion to take a robotic spacecraft to the icy moons of Jupiter. And that was a program that a lot of money was thrown at it. The Office of Naval Reactors was brought in to help develop the reactor for the spacecraft. But again, due to funding shifts and funding priorities, the program was defunded. And again, on the power side, for putting space nuclear reactors into operation, the two programs that go back again to the 50s were the SNAP program that lasted until 1973. And then you had the SP100 program that was the 1980s, 1990s program. But again, even though they've tested and developed numerous reactor designs, none has really ever been employed operationally, aside from that one tiny SNAP unit that was launched 55 years ago. So it's a really interesting issue. Why has the U.S. initiated, spent lots of money on, and then terminated these programs, not once, not twice, but 5 times? And will the current initiatives undertaken by Department of Defense and NASA, will they suffer a similar fate, or will they be the first time that we actually break through and get these technologies operationalized? So that would be a great thing, I think, for everyone concerned, but it's not really clear if that's going to happen. So it's a great discussion to have, and I look forward to having it with you, Pat. Thanks.
Thanks so much, Jim, for that history lesson. So if we look at where we are today, you mentioned we want to go to the moon. So obviously we need space power. We need space terrestrial power. We know that the Army is looking at Pele, which is essentially a forward operating base, FOB, for nuclear surface power. We know that space surface power, we have had what was previously called the kilopower, and now is called space fission power, that is being looked at for power on the moon and as we go further. But if we look at 2 areas, and I'll say nuclear electric propulsion, nuclear thermal propulsion, these are 2 different ways of using our nuclear or atomic neutronic power to get us to, say, Mars or even beyond. There's been a lot of discussion about, do we use nuclear electric? Do we use nuclear thermal? From an aerospace point of view, we'd say that it's not an either or, that there are places for both nuclear electric propulsion and nuclear thermal propulsion to assist us in getting to Mars. Jim, I was wondering if you have some comments about looking at these 2 and compare and contrast them.
Sure. So the basic technologies are in nuclear thermal propulsion. You're taking a very high temperature reactor, up to 4,000 degrees Fahrenheit. That's much, much, much higher than you have in your current fleet of terrestrial light water reactors that we use for electricity generation here in America. And you're pumping through this very hot reactor core liquid hydrogen, which comes in at negative 420 degrees Fahrenheit. And then when it hits the hot core, it expands very rapidly and provides a lot of thrust as it's expelled out the back end of the spacecraft. So it's pretty much a basic heat exchange type of operation where you produce thrust as the propellant gets expelled out the back of the spacecraft. The specific impulse you can gain from that is about twice that of a chemical rocket. Specific impulse basically measures the efficiency of an engine. So your basic chemical, the best chemical rockets are in the 400s of what's called seconds of a specific impulse. But with a nuclear rocket, a heat exchange rocket with a solid core type of heat exchange setup, you're looking at potentially having 750, 850, maybe 900, possibly as much as 1,000 seconds of specific impulse. And what that means is you can get places faster, you can carry more payload, and you can do it more efficiently. On the reverse side, if you look at nuclear electric propulsion, again, you use a nuclear reactor to create heat, which is then through a heat exchanger is used to expel ions out the back of the spacecraft. So you don't generate as much thrust, but it's extremely efficient. So for a long distance space mission, such as a robotic trip to Jupiter, such as what the Bush administration was looking at in the early 2000s, you get extremely high ISPs, possibly as much as 3,000 seconds or higher, which means, again, you have a very high efficiency for the spacecraft. So instead of doing a flyby like we did with the New Horizons spacecraft of Pluto, where they kind of just went zipping on past, you could go and loiter. The New Horizons was looking at between 4 and 6 years of scientific achievements in the vicinity of Jupiter, and a minimum of 2 months circling a couple of the icy moons. They were looking at really close explorations of Europa, Callisto, and Ganymede. So that's the sort of scientific heft you can bring to this by having a nuclear technology. It's just a lot more loiter time, a lot more efficiency in your engines. But again, the nuclear electric doesn't have as much thrust, but it does have a lot higher efficiency that makes it ideal for these scientific missions.
Thanks, Jim, for that. The other thing that we want to look at is that in nuclear thermal propulsion, we have the ability to abort, versus in some of the nuclear electric propulsion configurations, we don't have that. So there's pros and cons for each. But I think that both of us would agree that we need both. We need one if we want to go to very long missions, as you were talking about, or if we want to take cargo to Mars, for instance. However, the advantage of nuclear thermal propulsion is the fact that we get there quicker, maybe not as efficiently as nuclear electric propulsion. But the great thing about nuclear thermal propulsion is we can limit the harm and radiation to the humans as we take them from either moon to Mars or from the Earth to Mars. The other thing I want to talk about is people hear nuclear and get very upset about it. They think we're going to put off something on Earth that will be dangerous. One of the things, obviously, that we know that we have had RTGs that are used right now for very, very long missions. But one of the things that Aerospace has been looking at is the fact that for most of these nuclear missions, be they nuclear electric or nuclear thermo, is that we can't test them fully on the ground. So what happens then is that there needs to be very sophisticated modeling and simulation done of the neutronics, of the effluent, of how everything works together in both the fuel and the reactor and the engine. If we can model that, then we don't need what I would call a live test on the ground. Jim, we highlighted that this may be a negative, although modeling and sim might be able to take care of it. Can you help us understand where there might be other negatives besides just having a full-up nuclear test on the ground?
Yeah, I mean, the real potential drawbacks of nuclear, first, it's not cheap. Nothing in nuclear is inexpensive. At the same time, though, there's some really good news that's happened in the last few years. You mentioned the kilopower experiment and the crusty reactor that was tested out in the Nevada desert 3 years ago. NASA has been able to, working with the national labs, to really put together a prototype space reactor that at very low cost compared to some of these earlier programs. And part of that is because they're building off what has been learned over the many decades that we've been developing these technologies. So we're not ever starting from scratch. We're always taking the knowledge that's been gleaned and adding to it. So rather than spending several $100 million, this prototype was done, I think the number was around $20 million. So the whole cost equation might be in a positive tipping point, where we've done so much work on all the various aspects of nuclear space technologies, both power and propulsion, that we're kind of just fine tuning at this point and not really, doing the developmental research from scratch. You mentioned the testing conundrum. That is a serious issue. If you go back to Rover and NERVA, this is where we built and tested 20 separate reactors or nuclear rocket engine configurations in the Nevada desert. And we were venting the exhaust from those reactors right into the air. That's certainly nothing you're going to do now in the modern era. So you're going to have some sort of, confined testing capability that you capture all those exhaust gases and make sure that nothing bad gets out into the atmosphere. That could be a very expensive proposition. You're talking probably hundreds of millions of dollars, if not billions, to build such a facility. The Air Force, during the Timberwind project, actually designed one. I know there's work down at Stennis looking at potentially doing something down there, but those decisions haven't been made yet. There's also an option of taking a prototype and actually doing the first demonstration in space. In other words, you kind of skip the ground testing because of the very robust simulation and modeling that we now have with our computing power. And you go straight to a small demonstration project where you put it on orbit and you take off from there. So there's never any chance of any radionuclides getting into the atmosphere or any contamination concerns, anything like that. That's a pretty intriguing concept. Then the question becomes, if you're ever going to human rate these, can you do that just through in-space testing, or do you need to do instrumented tests here on the ground? And that's something that we'd have to see how that kind of plays out over time. But the idea of just kind of getting a prototype on the top of a typical chemical rocket, putting it into orbit and testing it up there where it really can't hurt anybody is a really intriguing opportunity.
Residing here at Marshall, who is the NASA premier propulsion organization, I think that what you were saying about robust modeling in sim, we do a prototype to work out some of the neutronics, some of the heat flow, some of the materials that has to be used, and then actually testing it in space is where Marshall is going in this direction. What's also interesting, we talk about both power and propulsion. The absolutely good thing about this is that the fuel and the reactor for both of them are highly complementary to one another. So development, both from a fuel perspective and from a reactor perspective, can help both the propulsion side of the equation as well as the power side of the equation. And that's I think the great thing about Glenn is working on the power side, but we're relying on our national labs at Idaho, at Los Alamos, and at Oak Ridge to help us with the fuel and reactor development. The other thing that I think has changed historically is that we now have a component of the industry that we didn't have before, and that's the commercial industry. We have individual organizations like BWXT, X Energy, General Atomics, USNC that are actually working on themselves, fuel, reactor, and then on the engine development, Aerojet Rocketdyne. So it's not only that the US government is investing in this type of development, but as in all space, we have individual commercial companies that have invested not only development, but in production and facilities for manufacturing. So I think that's a big shift from where we were, say, 20 to 30 years ago with NERVA and Rover. One of the other things I wanted to talk about is, we're at a point where the policy for the authorization for this kind of experiment, this kind of effort, this kind of task has really changed. And Jim, maybe if you could talk about where we are with the policy, where are we going, and what has to be done for really us to get set up from, we think we've figured out, and I don't mean to simplify it, the technical side of it, but there's also the policy regulatory side of it. So maybe if you could talk a little bit about where we are with that and compare and contrast with the technical advances that have been made.
Sure. As you know, last August, the president issued an executive order that basically devolved authority for approving launches of radioactive materials into space, basically to the agencies, with the real exception being if it's going to be highly enriched fissionable material that would require a presidential decision. Now, if you look at what we're actually launching into space today, it's really only radioisotope power systems, RTGs and RHUs that are used in things like the Mars Curiosity rover and missions such as that. That uses plutonium-238. It is not a fission type of process. It's basically just decay heat, where you're not controlling a reaction, so to speak. You're just taking the heat that this plutonium-238 produces, and you're converting that into electricity or thermal heat. And so that right now, under current policy, could be devolved down to the NASA administrator, basically. There's always interagency processes that go through. But you bring up a bigger point, and that is, where are we really going with this? Who's looking at this? You've got two entities right now, not just NASA looking at a surface reactor like kilopower for use on the moon. If you look at their 2021 budget request, that's what they specifically say that this surface fission reactor is going to be used for use on the moon. They're also doing fuel testing and fuel analysis for a potential nuclear thermal propulsion asset that would take people to Mars in the out years. But DoD is also looking at this through DARPA. They've got the Draco. It's the Demonstration Rocket for Agile Cislunar Operations. It's a great acronym. They're spending right now $10 million in fiscal year 20 funding, and they're asking for 21 million more. That's not a huge amount of money when you're talking things nuclear, but the fact that DARPA is looking at this on top of the work that NASA's doing is clear that this administration has placed a priority on at least investigating the potential uses of nuclear technologies in space. The previous administration, not so much. The Bush administration before that, they threw a lot of money at the Project Prometheus, which unfortunately you kind of peaked and then cratered out pretty quickly afterwards. That was a very innovative project that sadly didn't come to fruition. And then going back in time, it was really kind of hot and cold for over the years. The Reagan administration expended a lot of resources on space nuclear technologies, as did the Johnson, Kennedy, and Eisenhower administrations. And there were a few gaps in there where there wasn't a lot of money spent. So again, it's this cyclical, boom and bust phenomenon that, from just a policy point of view, is really fascinating to see how the government has kind of really embraced these sorts of technological development programs and then turn the cold shoulder and then wait a few years and start over.
Right. And you touched on a good point. If we talk about actually the type of fuel we're looking at today, using in nuclear thermal propulsion, nuclear electric propulsion, or even power, it's much different than we've looked at previously. If we look at a nuclear power plant, we have about a 5% enriched U-235. If we look at what the RTGs are they're plutonium. If we look at what the fuel that is being examined for our current efforts, it's what we call HALEU, or high assay low enriched uranium. So we're talking about an enrichment of 20% or less. People usually say 19.75. So besides just different entrants in the marketplace, as you say, DoD and NASA, and now we have commercial entrants, we're also talking about a different type of fuel concentration, less than 20% of enrichment, but we're also talking about a different type of fuel. One of the things that is being looked at for nuclear thermal propulsion that is being looked at for Pele, which is the forward operating base effort that the SCO, the Strategic Capabilities Office, is looking at, as well as DoD and NASA. Everyone's looking about this 19.75% of HALEU. But what's interesting is what the technological advances have been in the last couple of years. We're looking at what we call a TRISO, which is essentially a uranium pebble or pellet that's surrounded by silicon carbide, which is what the Pele, the FOB effort is going to look at. The next step we look at is this uranium pellet surrounded by zirconium carbide. So you're actually holding the uranium inside a chemical barrier so that the probability of leakage or exposure of the uranium on the outside is quite minimalized. And I think one of the things that we've seen from Rover-Nerva forward is productivity gains, but also gains in just the type of fuel and how to handle that fuel. Jim, do you see anything else in fuel going on in the next couple of years?
Great point, Pat, because the fuel is really the kingpin around which the whole thing is built. If you go back to Rover-Nerva, you had problems with fuel. You had a lot of vibrations created by the huge heat differentials, and they spent a lot of time designing the right type of fuel. When you go to the Timberwind, which was using actually what's called a particle bed design, you had literally millions of tiny particles of uranium with a similar to TRISO, where you had a coating around it, and then the hydrogen would pass between all these little tiny particles. And they had some significant technical challenges there that not necessarily were ever solved. The TRISO is fascinating because it's been around a little while. And a tri-structural isotropic fuel, it's pretty much safe in that you can't really melt down a reactor that uses it. But here's where a lot of these different initiatives all kind of might come into into the same brew and help a nuclear space program move forward. Is that like you said, a lot of these advanced reactor designers that are looking at terrestrial applications are going to be using TRISO. There are companies that are going to be making TRISO commercially. It's going to be kind of the coin of the realm potentially in the advanced reactor market for terrestrial applications. Well, if that can also be used for space, what a boon that is for the folks at NASA and the folks at DoD and DARPA who are looking for, the right type of tested fuel. Now, the question is, can it operate in temperatures as high as what will be produced in these small space reactors? I don't believe that's been proven yet, and so there's a lot of demonstration and qualification for fuels that needs to go on. But I think you're going to see a lot of synergy between what's happening at DARPA, what's happening at NASA, and what's happening at DOE when it comes to advanced nuclear reactor technologies.
Yeah, I totally agree with you. And that's why maybe I'm the optimist in this group, but I do believe a technology demonstration for something around 700 to 900 seconds, as you referred before, of ISP, thrust somewhere between 12.5 to 15,000 pounds will be achievable, can be achievable by 2026, 2027. And I think if we are to get to Mars, we're certainly going to need those. But as you correctly point out, what is needed in the short term for us to not just to go back to the moon with the first woman and another man, but also to be able to sustain on the moon. And that's really the goal, as far as I see it, is that if we're going to have a sustained presence on the moon, that we're going to need power on what I call terrestrial. It's not on Earth, but it's on the moon itself. So I think some of the things that are being done on the DoD side can help NASA. I think some of the things that are being done for NASA can help DoD. There has been some discussion between DoD and NASA. Obviously, they both have different goals. One is more concerned with space situational awareness. The other is more concerned with power either on the moon or on Mars and then getting us there efficiently. But I do believe there are two areas where they actually come together. The first we've talked about a lot. That's the fuel and the reactor and how that develops. Once you have that, then you sort of devolve into, well, do I want it for propulsion? Do I want it for power? Or there's even been some ideas about, I call it, bipolar. You'd have both of them in a particular satellite to where both of these can be used for space situational awareness. But I think, we start out together, maybe we devolve, but if we look where they might come back, this is in cislunar space. So both NASA and the DoD are going to be operating in cislunar space. And there's a lot of technologies and enabling functional areas that both of them are going to be needed in this area we call cislunar space. And that's why I think the combination of our national labs, NASA, DoD, and the industrial base community in this area are really going to be working together, put forward that all the achievements for everyone will actually assist others. In other words, something that works on DoD can be transmuted over to NASA or vice versa. And I think that this is one time where I believe that we'll have cross-pollination and good communication, because we can't get there alone, number one. No single agency, be it DoD, NASA, DOE, can fund it by themselves. So I actually think, because at least at the beginning and maybe the end of this value chain, that there is some cross-pollination that we will get there, but maybe I'm just an eternal optimist. So I don't know.
Yeah, and there's one other development that's been, I think, very important here is we now, again, have a National Space Council, and they are paying very close attention to this. If you talk to the folks on the council, they're very intrigued by the opportunities that nuclear power and propulsion offer to space exploration as well as DoD missions. So having them as kind of a supervisory role, looking over the agencies and making sure that these synergistic opportunities arise and are taken advantage of is a really important function of the council. And I think they're carrying it out pretty well.
You're right, Jim. I mean, if we look from a policy point of view, we've had changes. If we look for a technology point of view, we've had changes. And the Space Council has changed from a regulatory or providing a direction point of view. So that's why I think things are sort of lined up to where we may have an operational system. I've thrown out 2026, 2027. Jim, what's your betting on where the timing of where we might end up with something?
Well, DARPA is looking, at least in their published budget documents, to try to do a demonstration by 2025 of a small demonstration rocket using, it looks like, high assay low enriched uranium as fuel. That's a pretty aggressive timeline. I think Congress was pushing NASA to try to get a similar demonstration by 2024. Based on the current budget priorities, that might not be achievable. We'll have to see if that can be done. It's probably unlikely at this point. Because again, if you're working on a lot of, technical fuel issues to make sure that that's kind of locked down first, that might take a few years to get that done. But so it could be earlier than 2027. The other thing about this is it's not just these normal programs that we're looking at, if you can call them normal. We, again, have gotten nuclear thermal propulsion up to TRL-6, which is pretty close to being ready to demonstrate it in space. There's also some of the more arcane ones. I don't know if you want to talk about them, but for example, nuclear pulse propulsion, which was tested back in the early 1960s, an absolutely fascinating concept that even today some people think holds the best prospects for rapid transit out to the outer planets.
So Jim, if I had to pin you down, I mean, I'm saying 26, 27. When do you think we'll see a nuclear demonstration of power or propulsion that's not on the Earth, either being launched or being somewhere on the moon? When is your betting that might come across?
Well, I would hedge the bet by saying that's all going to depend on the grander politics of things. Right now, you have an administration that's pursuing these sorts of capabilities. And so 2025 is not off the table. It's certainly achievable. But as they say in political science, you really need three things to kind of come together for these sorts of things to happen. One is you have to have a problem that you're trying to solve. Second, you have to have a solution at the ready. And the third is you have to have like the political environment for this to happen. Look at the changes America has gone through in the last 3 months with both the COVID virus and the unrest we've seen in some of our cities over various issues. I mean, America's policy environment can change fairly quickly in directions you can't necessarily predict. So if there's a change in administrations, whether in 6 months or 4 years and 6 months, that isn't interested in this, or even if there's other priorities that come up. If you look back at the Prometheus project that Administrator Sean O'Keefe was really, pushing forward early in this century, one of the things that got in the way of that, really two things. One was the fact that the International Space Station was way over budget, and that budget needed to be reined in. And that was a hard fight between ISS money and developmental money for the Prometheus nuclear electric propulsion technology. But second, you had the space shuttle that we lost, and we had to return to flight, the Columbia, and that was a horrible tragedy. But it really consumed a lot of the time, effort, and funding coming out of NASA. So those are the sort of unpredictable things where you don't really know. Again, hedging my bets. I think it's perfectly achievable by 2025 to 2027 timeframe if the politics keep pushing forward and you've got a lot of leadership coming out of the administration to keep this as a top priority. Because if it's not a top priority, it's not going to happen.
I very much agree with you, Jim. Working in the program and project offices, sometimes it's the technical that's the easy part, and we say the politics is the difficult part. I'm also the one that says politics is equals economics, and economics is equal to politics. So we've got the money side of it, we've got the advocacy side of it, and then of course we have the technical side of it. Now, being a chemist and a project manager, I like to think that we can solve the technical problems. I'll leave the politics and economics to someone else. So we're just about at our time here. Thank you so much, Jim. Is there something you'd like to say to just close us out this afternoon?
Yeah, I would encourage folks to go online and take a look at some of the YouTube videos about the nuclear rocket tests that were conducted, both for Rover and Nerva. There's plenty of footage available. It's fascinating stuff. The Kiwi A experiment in 1959, where they actually lit off the very first microreactor to potentially use in space applications. And also look at what happened in Project Orion, which was this idea of using nuclear bomb blasts to actually propel a very large spacecraft into orbit. There's some fascinating footage also you can look at from some tests they did with conventional explosives, trying to launch a prototype, a couple hundred yards up in the air. But it's called the nuclear pulse propulsion theory that is, quite frankly, pretty entertaining thing to learn about, and quite frankly might be something that could be operationalized someday. Obviously not from planet Earth, but you'd have to do it in orbit. But those are the sorts of videos that are out there just to show that a lot of progress has been made in these technologies. The question is now, do we have the kind of the political will and the right circumstances, the right funding streams to put them into place operationally.
Well, thank you so much, Jim, for spending this time with us. And I'd like to say, no matter how we get to the moon or how we get to Mars, aerospace, with our long history in propulsion, will probably be there, be it nuclear electric, nuclear thermal, or who knows what will come out for our next energy effort in the years to come. So thank you, Jim, and thank you to Rebecca, and over to you, Rebecca.
What an interesting discussion we had today. Thank you both so much for being here. As always, we are so happy to have these exciting topics and people to talk about these fascinating different types of subjects. Engage with us, ask your questions on Twitter. We're at #TheSpacePolicyShow. You can also find us at aerospace.org/policy. Again, put your questions in the video comment box below, ask questions on Twitter, engage with us in whichever way you can. Until next time, take care.